Welcome to The Explainer. Today, we're looking at something literally mind-bending. We're exploring a framework that attempts to solve one of the most stubborn, frustrating mysteries in all of modern physics. We're diving into Dr. Ahmad Rihan's radical unifying theory of quantum mechanics. For decades, the massive gap between the chaotic, unpredictable quantum world and our smooth, predictable classical world has completely puzzled scientists. It's like they're playing by two completely different rulebooks. Well, Dr. Rihan's interpretation proposes a realist cyclic account that seamlessly connects the two, uniting quantum weirdness, atomic structure, and even cosmic organization into one single mechanism. Okay, let's dive into this. To really wrap our heads around this theory, we need a roadmap. We're going to start by rethinking quantum collapse. Then we'll break down the mathematical engine driving all this, called the Faraday quarter solution. After that, we'll peek inside the Rihan atom, zoom way out to cosmic bubbles and filaments, and finally look at how we can actually test the theory. All right, let's get into section 1, rethinking quantum collapse. To understand why Dr. Rihan's theory is such a huge game changer, we first got to look at the historical elephant in the room, the standard view, usually called the Copenhagen interpretation. For nearly a century, we've been taught that at the quantum level, particles exist in this hazy blur of probabilities, a wave function, until an observer actually measures them. And then, at that exact moment, bam, the wave function supposedly collapses into a definite state. But this standard idea is super messy. It relies on an invisible, totally unpredictable, irreversible collapse that seems to happen magically just because we decided to look. But what if we've been misinterpreting the data this whole time? What if quantum collapse isn't actually random at all? What if there is no magical observer effect? And this brilliantly illustrates the core difference. On one side, you have the standard view: random, observer-triggered, irreversible. It's basically a one-way street from quantum potential to classical reality. But then, look at the Rihan interpretation. It argues that the wave function is actually physically real, and its evolution is deterministic, cyclic, and 100% reversible. Dr. Rihan posits that what we think of as a random collapse in the lab is actually just us sampling a system at a very specific, predictable moment in an ongoing, continuous cycle. So there's absolutely no external observer required to force reality into existence. Moving right along, Section 2, the Faraday quarter solution. So how exactly does this continuous cycle create the reality we experience? Well, don't let the heavy physics jargon intimidate you here. Let's break this down. Imagine a ticking clock, but instead of ticking seconds, it ticks in 90-degree angles, what mathematicians call intervals of pi over 2. Dr. Rihan calls these Faraday quarters. According to the theory, the wave function is constantly rotating through an internal phase space. Every single time this rotation hits a 90-degree mark, the wave function undergoes a deterministic projection onto the real axis. In plain English, this ticking 90-degree clock systematically churns quantum potentiality into definite, classical-like outcomes. Let's move to the mechanics here and see how this builds. Think of Euler's identity acting like a bridge. Step 1, we hit a real quarter. The amplitude is purely real, meaning the system is in a definite classical configuration. It's solid, it's something we can measure. Step 2, the clock ticks 90 degrees to an imaginary quarter. Here, the real projection vanishes. The system becomes purely imaginary and is, momentarily, totally unobservable to our classical instruments. Step 3, the cycle just repeats. Because the underlying process remains unitary, it's completely reversible. We aren't destroying the wave function when we measure it. We are just catching it on a real quarter beat. And this brings us to a really profound shift in the math itself. In standard quantum mechanics, the imaginary unit I in the famous Schrödinger equation is usually just treated as a handy little math trick for calculating probabilities. But in the Rihan interpretation, oh man, it turns out I is physically real. It represents an actual physical 90-degree rotator. This rotation directly mirrors the phase relationships we see in classical electromagnetism, specifically Faraday's law, which involves his exact same 90-degree shifts between electric and magnetic fields. This means classical physics isn't some separate set of rules. It's simply the real axis shadow of this continuous complex rotation. Okay, section 3, inside the Rihan atom. Now that we have a grip on the math of this cyclic clock, let's zoom out a bit and see what happens when we try to build matter with it. If reality is ticking in Faraday quarters, what does a single atom actually look like? Well, the Rihan atomic model, or RAM, offers a fascinating picture. Actually, scratch that. It's more like a completely new paradigm. Instead of the traditional rigid shells or little orbiting point particles, RAM describes atoms as equilibrated protonic and electronic Gaussian surfaces. Picture them as soft, squishy, overlapping probability clouds that can continuously deform. And what holds them together? A strict condition called the net momentum velocity, or NMV balance. As the relative phase between the proton and electron advances and hits a Faraday quarter, this NMV balance forces a momentary realignment of these soft surfaces. That flash of realignment is what we perceive as the localization of an electron. And wonderfully, the math behind these soft, vibrating surfaces perfectly recovers the classical Bohr-Rydberg transition series we observe in nature. And here is where RAM gets incredibly elegant. Look at this number, roughly 137. Well, 1 over 137 to be precise. In physics, this represents the fine structure constant. It dictates the exact strength of the electromagnetic interaction, and honestly is usually just plugged into equations as a given, unexplained external input. A total mystery number. But in the Rihan atomic model, this dimensionless constant isn't arbitrary at all. By calculating the stationarity of the action of those spherical Gaussian surfaces we just talked about, RAM actually derives the observed order of magnitude of the fine structure constant purely from the geometry of the atom itself. It also recovers the proton-electron mass ratio. It's an absolutely stunning mathematical victory for the theory.
Which brings us to section 4, cosmic bubbles and filaments.
We've looked at the tiny atom. Now, let's zoom out to the ultimate macro scale. Now, what's really interesting about this is the sheer, sweeping ambition of the claim. Rihan is literally uniting Einstein's special relativity with quantum mechanics. In this framework, spacetime isn't just a boring, empty void. It is permeated by a dynamical network of electromagnetic filaments. Photons, particles of light, travel by executing continuous helical or spiral windings around these filaments. And all of this exists within a giant hierarchy of nested bubbles, where the walls of the bubbles are basically defined by local mass and energy. What this all means is that the universe is entirely self-similar across all scales. It's fractal. Because mass is the complementary opposite of energy, massive bodies follow a reversed helical geometry compared to those photons. The central mass defines the axis, and orbiting masses spiral around it. And this exact same organizing principle scales up seamlessly, from a tiny electron string vibrating in an atom to our entire planetary system, all the way up to sprawling galactic cosmic webs. They all share this helical, nested bubble structure. Even the universal speed of light, c, isn't just some arbitrary speed limit handed down from nowhere. It actually emerges as a natural topological consequence of this filament geometry. All right, the final piece, section 5, testing the theory. It is a majestic picture of the cosmos, for sure. But hey, in physics, beauty just isn't enough. A theory absolutely must be testable. So the crucial point is that this isn't just armchair philosophy. The Rihan interpretation offers concrete physical tests we can run right now in a laboratory to prove or constrain these massive claims. For example, we have the phototropic fabric strain test, which measures physical shear strain produced by a focused beam of light on a soft suspension. There's energy-dependent clock acceleration, predicting that if you illuminate one super-precise optical clock and shield an identical one, a fractional phase difference will literally accumulate between them. We can even test for helical photon group delay in metamaterials, or measure illumination-induced torque on a suspended membrane. Any statistically significant detection of these specific phenomena would strongly support this underlying helical geometry. The Rihan interpretation leaves us with a breathtaking paradigm shift. It replaces that random, chaotic quantum casino with a beautifully smooth, deterministic clockwork that scales from the smallest atom to the largest galaxy. So I want to leave you with this question to ponder as we wrap up. If our reality is just a continuous, cyclic projection of nested bubbles, what does that mean for our place in the universe? It kind of suggests we are intrinsically connected to the cosmos, right? Not as outside observers triggering random collapses, but as actual participants in a grand, unified, and beautifully geometric cycle. Thank you so much for joining me for this explainer, and keep questioning the nature of our reality.